This is not a pharmacokinetic buffet. This is more like a little sampler. It's kind of like the charcuterie plate of pharmacokinetics. We're going to talk about bioavailability, bioequivalence, and then we'll talk about volume and distribution and use one formula with that. So it's a little introduction to that. So the calculations weren't hard, but I will say until the concepts make a little sense for you, it's a little bit harder to set up. So make sure, let's go through these together, and we'll do these. These aren't too hard. The first topic, the questions 1 and 2 are just about bioavailability. The ability of a drug to go from the drug dosage form, whether it's a tablet, a capsule, a liquid, a suspension, a topical cream, or whatever it is, to go from the dosage form it's in, into the body, through the body, and into the blood. Okay, and while the drug can be the same in different dosage forms, the ability to get out of that dosage form and that ability for the dosage form to get the drug into the blood can vary. So here's an example of that when we talk about a couple of different extended release formulations. So the drug hyoscyamine is available in 0.25 milligram immediate release tablets, and that is dosed every 4 hours. Okay, those basic immediate release tablets have a 90% bioavailability. Basically, that means that 90% of the drug dose makes it into the blood. So bioavailable means regardless of what you give and administer, how much gets to where it needs to go. And in this case, we're saying into the blood, because once it gets into the blood, then it can go wherever in the body it needs to go. So to get into the blood, only 90% of it gets through. Okay, that's the immediate release tablets. If we have extended release capsules and tablets, so they're extended release, one dosage form is a capsule, one is a tablet, but they're both extended release, and they are formulated to release a dose of 0.375 milligrams of the drug at a controlled rate. So you only have to do that every 12 hours instead of every 4 hours. So you're going to do that every 12 hours. However, the relative bioavailability reported is 81 and 92% respectively to that of the conventional tablets. And this language is taken exactly out of what you would find in something like Lexicomp, where they're reporting the information either from the package insert or from the manufacturer. So it's a little confusing. So the 90% wasn't relative bioavailability, it was an absolute bioavailability. But the 81 and the 92% are relative bioavailability relative to what? The original dosage form. So you'll see that where things can get a little bit confusing. So let's step back and do one thing at a time. The first part of this question says, what is the total daily bioavailable dose in milligrams of an oral 0.125 milligram immediate release tablets given every 4 hours? So if you're taking the standard dose, what is the daily dose that gets into the blood? So go ahead and calculate that. I'll give you just a minute or two. These are pretty straightforward little snippets of each question. We'll do one thing at a time. So the first thing we want to know, with the reference dosage form, which is the immediate release, if it's dosed normally, then in a day or in 24 hours, how much drug actually makes it into the blood? Not just what's administered, but what actually makes it into the blood from that dosage form. The way that I did it here was to first kind of figure out how many doses per day. So, and you can do that however you want. Every 4 hours means in 24 hours, if you give something every 4 hours, how many doses per day? Is that what's 24 divided by 4? 6. So basically every 4 hours means they would get 6 doses in a day. So that's why you get 6 times the dose in milligrams. So again, hours cancel, tablets cancel. When you do 6 times 0.125, we're in milligrams. So that's the total amount per day. But this 90%, and I'm going to do this through the whole lecture here, and you don't have to do this in your math, but I want to make sure I understand. When we say 90% bioavailability, I always worry about you guys really understand. I know you just multiply by 0.9, which is 90%, and mathematically that's correct. But 90% bioavailability means, since a percent is per 100, it means that 90 milligrams does get absorbed. 90 milligrams out of how many? Out of 100. So for every 100 milligrams administered, 90 milligrams gets absorbed. So I'm just trying to help you visualize what the 90% bioavailability means. Okay, mathematically, we just take that total and multiply by the 0.9, which is 90%. And on a daily basis, using the immediate release tablets, we are getting 0.675 milligrams of hyoscyamine. Okay, so far so good? So that's kind of the reference dose. So that's what we're trying to compare the other dosage forms to, because would you agree, taking something 6 times a day is a pain. I mean, trying to remember to do that is going to be very difficult. So would it be easier just to take something twice a day? Absolutely, but that's only going to work so long as it gives us about the same amount of drug as we need on a daily basis. So let's move on to then what do we get with the extended release. So the question says, what is the bioavailability factor of an extended release capsule? All right, so the bioavailability factor is essentially just the percent expressed as a decimal, so not as a percent but as a decimal, of the bioavailability. So in this case, the trick is here, and I'll go ahead and just work this one and then you'll use it. The bioavailability factor for the capsules, make sure you know where the capsules, means that we're going to take the original immediate release 90%, and we said that the capsules are 81% respective to that of the conventional tablets. So basically 81% of the original 90%. And that's what I meant about them giving you not an absolute bioavailability, they gave you a relative to the immediate release. So compared to the immediate release, it has 80% of the, or 81% of the immediate release. So don't make that harder. If our immediate release is 90% and we're only getting 81% of that, basically just take 0.9 times 0.81, or what is 81% of 0.9, if you will. And that comes out to be 73, or 0.73. All right? Does that make sense? We're just taking basically 81% of 90, okay? And that percent, though, understand when we say bioavailability factor, they just convert the percent then to an actual decimal. So the factor is not expressed as a percent, it's in an absolute value. In this case, is 0.73, but that means basically means 73%, all right? Which is just 73 divided by 100. So is everyone okay where that one came from? We just took the 81% of the immediate releases 90% and got 73%, and then the factor then is 0.73. Now that we know that, we can calculate, doing the same thing we did really with the first original one, what is the total daily bioavailability dose now of the extended release capsules? We just calculated its bioavailability at 73%, or a factor of 0.73. We know it's dosed at 0.375 milligrams every 12 hours. So go ahead and do the same thing we did for the immediate release, but make sure you're using the new strengths and the new number of doses per day and its unique bioavailability factor that we just calculated. And tell me, what is the total daily dose? I'm hoping it's close to, as close as possible, to the original immediate release, but it certainly will not be the same. Clearly will be less, since the bioavailability is less. Okay, not make this too difficult. Again, how many doses per day in 24 hours if we're giving it every 12 hours? And clearly we're getting 2 doses per day. All right, so then 2 times 0.375 milligrams per capsule would give us the total daily dose. But remember, we're only going to absorb 73% of that. I mean, we only get 73 milligrams out of every 100 milligrams we administer. So when we multiply it by that bioavailability factor, we see that a total is 0.548 milligrams, 0.548 milligrams, compared to our, what was it, 0.675. So definitely less on a daily amount than we were getting with 6 of our immediate release tablets. So the capsules, I'm thinking capsules, I'm not loving that. What about the tablets? Do you think the tablets are going to be any better? I'll let you do this. This is what we just did for the capsules in terms of just calculating the bioavailability factor. So remember, see if you can determine if we're taught reference as the immediate release tablets, but now we're talking about the extended release tablets. We said their relative bioavailability was 92%. So calculate for me now the extended release tablets' absolute bioavailability, not its relative bioavailability. Did you get 0.83? I just did that by taking 90 times 0.92, okay? So basically 92% of 90% gives me an absolute bioavailability of 0.83 for the extended release tablets. So now let's calculate the daily dose of the tablets. Do the same thing we've done now twice. Calculate for me, knowing that the tablets have the same strength of 0.375 milligrams. They're still given every 12 hours. but they definitely have a different absolute bioavailability. So go ahead and use that and calculate its daily dose. See if we like it better. You get my final value of 0.623 milligrams. And finish up if you need to. Again, it's 2 doses per day times the 0.375 milligrams for the total daily. But again, at 80% or 83% or 0.83 bioavailability factor means there are 83 milligrams absorbed for every 100 milligrams administered, and that's where I got the 0.623. So if you had to recommend to a prescriber for whether you're going to recommend the extended release capsules, the extended release tablets, which one would I recommend that you recommend? The tablets. And the main difference there is they have better bioavailability. More of the drug is going to get into the blood to do what it needs to do, and will be closer to what you get by giving the immediate release tablets every 4 hours. So that's would be why in different dosage forms have different bioavailability. Because extended release especially, it's the mechanics of the dosage form, how they actually get that extended release to work. And so they don't all have the same bioavailability. All right, so far so good? Let's move on. I like this question, so hopefully you have a little more visualization on this, because most of you maybe realize an inhaler, a very important inhaler for all asthmatics and COPD patients for an immediate relief, a bronchodilator, is albuterol. So that's a rescue inhaler. So what you may not have realized, and this is true, albuterol is a drug used to treat, as I mentioned, comes in inhaled dosage forms as an inhaler, but it comes in tablets and syrup as well. So it can be administered orally. It's just more rapid acting when you give it to an inhaler directly into the lungs. However, what you may not have realized is that, and we're going to do this in lab, right? We're going to show you how to correctly counsel on using a meter dose inhaler, okay? Exhale, take a big breath in, put it in, do all of those steps to try to maximize how much of that aerosol that comes out ends up where? Where do you want the drug to end up? In your lungs, right? Where it can work immediately. But guess where a lot of it gets sprayed? Onto your cheeks and your mouth, and then what do you do with it inside there? Your saliva gets in it and you swallow it. So what we're saying here is that it's postulated that 90% of that spray that you spray to try to suck into your lungs actually gets sprayed into your mouth. It doesn't go to waste because eventually you will absorb it through your GI tract, but only 10% actually gets into the lungs. All right, so we actually have a dosage form where that albuterol, 10% gets into the lungs, 90% goes in through the GI tract. However, the bioavailability of the drug is different through the lungs as it is through the GI tract. So to try to calculate how much albuterol actually makes it in from a single dose, if you will, is more challenging. We're going to have to account for drug coming from both locations. And that's what we're trying to do. And to illustrate my thing about the bioavailability, realize I say in the question there that albuterol has an F oral. What does F stand for? Bioavailability factor. So the bioavailability factor for the oral is 0.9. If you wanted to express that as a percent, what is 0.9? 90%. So 90% of albuterol gets absorbed through the oral tract, whereas only 83%, or an F factor of 0.83, gets absorbed through the lungs. All right, so let's keep that in mind. So let's start with this. Oh my gosh, it's a review of the last chapter. Let's see how well you do. Question number 1, it says, what is the weight in micrograms of albuterol in 2 sprays, 2 inhalations, if the inhaler delivers 108 micrograms of albuterol sulfate per spray? So we have, what do we have? We have, which one is the moiety? Which one is the compound? Set up the proportion of the molecular weights, and you can solve for the actual equivalent weight of what we want, which is the moiety. We're asking for albuterol, the moiety, how much of that when we have 108 micrograms of the compound albuterol sulfate. So you didn't know you're going to get a pop quiz on this, right? So let's try it. See if you can set up that proportion and determine the equivalent amount of pure albuterol from 108 micrograms of albuterol sulfate. So keep in mind also it did ask for 2 sprays. So it's 108 micrograms per spray. What is 108 times 2? 216. So understand my 216 here comes from 2 sprays, or 108 times 2. So 2 sprays is 216 micrograms of albuterol sulfate. Here is my moiety molecular weight, Here is my compound molecular weight, so I set up that proportion, set up the weight of my compound in the denominator on that side, solve for x, and I got 180 micrograms. Okay, 180 micrograms of albuterol. Ready to move on? So all of that tells me now that's my dose. That's how much is going to go into my body, but it's going into two different places. All right. So now this question wants to say, okay, given those two sprays or those 180 micrograms, what weight of albuterol in micrograms is absorbed via absorption into the lungs? So tell me, of the 180 micrograms, how many micrograms go into the lungs? Not a hard math calculation as long as you know what to use to do that. So how do I know what amount is going to get into the lungs? There's two numbers you need to consider. This percentage and this bioavailability factor. There's two things to consider there. Remember, not all of the drug makes it to the lungs, so you got to find out the amount of drug that makes it to the lungs, and then not all of that is going to make it into the blood. So there are two steps. Into the lungs, and then from the lungs into the blood. So two mathematical computations there, if you will. So I'm starting with 180 micrograms. What fraction of that makes it into the lungs? I wasn't told that. I was told how much makes it into the GI tract. But if 90% makes it into the GI tract, what percent then makes it into the lungs? 10%. So you had to factor in that if 90% goes into the oral, then 10% goes into the lungs. So again, I'm just expressing that 10% in ways that hopefully it makes sense. When I say 10% makes it into the lungs, that means 10% of what's administered, or 10 micrograms out of 100, gets inhaled. Okay, so if you give them 100 micrograms, then only 10 micrograms makes it into the lungs, 10%. So again, if I multiply 180 by 10 and divide by 100, I now know the number of micrograms in the lungs. All right, all I factored there is the 10% of the dose going into the lungs. Okay, so of that amount, remember, only 83% is going to get absorbed because the bioavailability across the lungs is 0.83, which is 83%, meaning 83 micrograms will be absorbed for every 100 micrograms inhaled. So again, that will cancel the inhaled micrograms, and if you multiply all that across, basically 180 micrograms times 10%, times 83% gives you 15 micrograms. So of the 180, only 15 micrograms gets into the blood from the lungs directly. Okay? So and again, for the sake of time, and since some of these calculations are very similar, I'll kind of work through those. The next question wants to know, okay, how much actually gets absorbed from the GI tract? So we'll start with the same original dose, the 2 puffs, the 180 micrograms is the same, but now we can use our 90% since I know that is the amount from the oral format through the GI tract. So I want 90% of the 180 micrograms to go into the stomach, and then again, my F value for the oral route is 0.9 or 90%. So 180 micrograms times 90% times 90% gives me 146 micrograms total. That's the amount of albuterol that will hit the blood from the blood. Does it tell you when it hits the blood? No. Here in a little bit, the other thing that we're going to do in pharmacokinetics is talk about timing and how long. So again, it is going to get into the blood much more quickly through the lungs. It'd take longer for this 146 micrograms to hit the blood, but eventually that amount will. All right. So then in the end, if we administer 180 micrograms in 2 puffs, what's the total dose of albuterol that eventually gets into the blood? The 15 micrograms from the inhaled plus the 146 micrograms means we only actually get 161 micrograms of the inhaled 180 microgram dose. 161 is the amount that will actually be able to produce a therapeutic effect in me, which means it got into the blood. All right. Bioavailability. Let's move on to a different topic. It's still bioavailability, but we're going to call it bioequivalence. Bioequivalence is the idea that if you take a dose, and you've seen this, if we take the dose times its bioavailability factor, you can see how much gets into the blood. All right, that is how you get a therapeutic amount. Well, how can you compare different dosage forms that release at different bioavailabilities to make sure they do provide a bioequivalent dose? Equivalent means that the dose times the bioavailability factor of one product is the same as or is equivalent to the dose times the bioavailability factor of another product. So basically this formula right here. You're going to see this is not particularly difficult, but essentially we're saying for one product, if you take its dose times its bioavailability factor, that's how much gets into the blood to be equivalent. The dose times the bioavailability factor of the other product has to be equal. So let's just set these things equal. Bioequivalence. All right. So if the bioavailability factor is 0.5 for a suspension, okay, and is 0.375 for a tablet of the suffixing in the question. I know I cut off a little bit of the question there, but here we have a F and of one dosage form and an F of another dosage form. It wants to know what is the bioequivalent dose in milligrams of the suspension to that of a 400 milligram tablet. So would you agree I have a dose and a bioavailability factor? So again, if I wanted to say the dose here, the factor here, I know the bioavailability factor of the suspension, I just don't know the dose. So I'll give you a second here and see if you can solve for the dose of the suspension that gives you the same amount as the dose of a 400 milligram tablet given different bioavailability factors. What is the bioequivalent dose of the suspension? Not sure I said that wonderfully. But just use that formula. It's not a hard formula. Again, the math for this class on pharmacokinetics, since we don't spend forever in teaching you the background, is supposed to be fairly straightforward. So bioavailability factor times the dose of one dosage form is going to equal the bioavailability times the dose of a different dosage form if they are bioequivalent. Again, what I started with on the left-hand side of my formula is the F factor, the bioavailability factor of the tablet, 0.375. And we know its dose is 400 milligrams, okay? So essentially, if I do that math right there, that comes down to 150. 0.375 times 400 milligrams is 150 milligrams. We're gonna set that equal to the bioavailability factor of the suspension times X, because I wanna know what dose of the suspension will equal what I get from my tablet. So again, that 150 milligrams is equal to 0.5X. 150 divided by 0.5 is 300. So is the amount, the dose from the suspension, higher or lower than the dose for the tablet? Lower. Why can it have a lower dose and yet still produce the same amount in the blood? Because it has a higher bioavailability factor. More of the drug gets in from the liquid than it does from the tablet. So you don't need as much of the dose from the liquid to equal what you get from the tablet. The bioequivalence, you're trying to make one equal to the other. All right? So now, this is easy breezy. What volume of suspension do you need to provide that bioequivalent dose? We said we needed 300 milligrams. This is a no-brainer. Quickly tell me what volume of suspension. Because I know it in milligrams, which is great, 300 milligrams, but to dispense it, you would need to know the volume of the suspension to tell the patient to consume. Because it's 300 milligrams, you just divide by the concentration here, provided here, which means multiply by 5 mils over 100 milligrams. Milligrams cancel, and 300 times 5 divided by 100 gives us 15 milliliters. So that is the volume equal to a 400 milligram tablet. So if you can take one tablet of 400 milligrams or 15 milliliters of this suspension, and you would get the same therapeutic effect. All right? Now, here's a little deal. They also come in capsules. Suffixing comes in tablets and capsules. It says the capsule is bioequivalent to the tablet under fasting conditions. However, if somebody were to take this capsule after a meal, the food decreases the absorption by approximately 15%. So what is a bioequivalent dose in milligrams of this 400 milligram capsule if taken with food? So what is it if it's taken with food? Well, what is food going to change? Food is going to change its bioequivalent factor and reduce it by 15%. All right? So we know that The dose is the amount taken times its factor. So here is the factor from the tablet. We said it was bioequivalent under fasting conditions. So it was 0.375 was its tablet's bioavailability factor, and the strength was 400 milligrams. So here is the F times its dose. So we would just multiply that and get essentially what we did already, which was 150 milligrams. But remember, we are going to reduce that by 85%. And that is the trick here. Realize you don't multiply by 15% because it's a 15% what? Reduction. If it's a 15% reduction, then what remains is 100 minus 15 or 85%. So this is always a trick for you guys on exams. Remember, if I give you a reduction, it isn't important to know how much it was reduced by. It's important to know how much is left. That means when I'm done, if it's reduced by 15%, what I have left is 85% of that dose. So here's the dose times the 85% due to the food, and therefore its amount would be 128 milligrams. Okay? All right. So we've done bioavailability and we've done bioequivalence when you kind of set the F times the dose equal to each other. All right, let's move on. We'll totally ignore all of that for now. And let's move on to the other kind of main topics. I need to make sure you understand on how to do a little bit of math with volume of distribution and the formula that says the dose is equal to the volume of distribution times the CP, plasma concentration. Okay, so let's just use some of this here. So in this question, we have a 47-year-old male who weighs 141 pounds, seen in the emergency room due to a panic attack, which some of you might be experiencing now. But anyway, so let's just say there he's got a panic attack. The physician prescribes 4 milligrams of lorazepam to be given by IV push. Okay, the drug is commercially available as a 2 milligram per ml injectable solution, and the volume of distribution for lorazepam is 0.89 liters per kilogram. So I've given you a volume of distribution that's in liters per kilogram. So let's use this. So instead of me trying to lecture to you on this, because I hope you already have a little bit of the background. If not, watch some of my videos. They do a little more detail, but let's use some of this to answer the question. The first question is straightforward. What volume in milliliters of the injectable solution is needed to provide the 4 milligram dose? And this is so simple, I'll just tell you. So again, we want 4 milligrams, so there's the dose. The concentration of the injectable solution is 2 milligrams per mil. So if we multiply it by every 1 mil has 2 milligrams, clearly we want 2 milliliters. Is everyone okay with 2 milligrams per mil? If we need 4 milligrams, we need 2 milliliters. Easy breezy. Now this is where it gets a little bit weird because you can't just inject the solution by itself. The instructions are to dilute it with an equal volume of compatible diluent. So we'll just say sodium chloride. So we cannot just inject our 2 milliliters. We need to dilute it, okay, with an equal volume of the sodium chloride and administer it at 2 milligrams per minute. So what I want you to do here is, and I'll give you a minute to do that, I need you to convert 2 milligrams per minute, which is an infusion rate, 2 milligrams per minute, but we need to convert it into mils per minute. So instead of milligrams, we need to convert the rate to milliliters. So use the fact that what we know about this in terms of what we're going to have to do to dilute it and convert milligrams per minute to milliliters per minute. So if you can kind of figure out how to do that. And start with 2 milligrams per minute. Then convert that milligrams in the numerator to milliliters. So figure out a factor. You need to convert, given your solution, how many milligrams are in your solution, how many milliliters are in your solution. That's how you can convert from milligrams to milliliters. It's the only thing missing. I'll give you a hint here. I know the dose is 4 milligrams. That was the whole point. So all I need to know is my 4 milligrams has what volume? What volume am I administering to provide the 4 milligrams? Hopefully you can see when you look at my answer here that this is not a mathematical challenge, but it is a mental challenge to kind of visualize what's happening here and how to convert your units. So as I said, we want to administer it at 2 milligrams per minute. That was given to us. What we need to know is that our dose was 4 milligrams. How many milliliters of the injectable solution did we just calculate that we were going to need? What did we get on this answer here? 2 milliliters, right? We determined 2 milliliters. But what did this say to do? with an equal amount. So we have to take our 2 milliliters and add an additional, exactly the same amount, 2 milliliters of sodium chloride. So in the end, what is my total volume? 2 plus 2 is 4. So there are 4 milliliters containing 4 milligrams. So that's how I can convert milligrams per minute to milliliters per minute. And in the end, what I need to infuse this is at 2 milliliters per minute. Okay? Well, I wasn't even pharmacokinetics at this point, but now we know what we're doing. Now let's talk about determining when we do something like that, when we inject a drug that has a dose, how much dose actually total ends up in the body, okay? You can do this outside of the bioavailability factors we talked about. And it starts with the volume and distribution. So here's the deal. The first question says, this one says, what is the patient's weight in kilograms? So it's 141 pounds. Let's convert that to kilograms. Let's not make a big deal out of that. 141 divided by 2.2 means, okay, this is actually a 64 kilogram patient. Now that I know this weight and I know that relationship for the volume of distribution, I can determine a patient-specific volume of distribution. A volume of distribution for lorazepam of 0.89 liters per kilogram isn't patient-specific. So let's find out what it is exactly for this patient. So we got their weight in kilograms times 0.89 liters per kilogram says that this volume of distribution in this patient is 57 liters. That is, lorazepam, when you give a dose of lorazepam, it appears to disperse in a volume of 57 liters. It's not a real volume in your body. There isn't 57 liters in your body. It just, compared to the blood, seems to leave the blood and go into a space that occupies 57 liters. Okay? So now we have its volume of distribution. Why is that important? Because I know this formula, oh, don't do that. I have this formula right here that says that the plasma concentration you will get, this is kind of cool when you think about this. When you give that 4 milligram dose, now I can predict what the concentration in your blood will be. Because have you already talked a little bit about how drugs need to have a therapeutic concentration? When drug concentrations are too high, what do they become? Toxic, right? They can cause all sorts of problems. And if blood concentration levels are too low, they may not be therapeutic. So what will the concentration of this be? Well, I can use this formula to find out. The only problem, and on my test, I will give you this formula. You don't have to memorize the formula. It's all about units. You have to match your units. Because here I want my concentration expressed in. And different drugs need different concentration units that they're normally expressed in. This is in, oh my God, what does that N stand for? Nanograms. So we need it in nanograms per milliliter. All right, this is an easy one to start off with because how much did we say we gave this guy? 4 milligrams. We know the dose. The dose is 4 milligrams. We just calculated the volume of distribution at 57 liters. That's your answer. That is your drug concentration expressed in milligrams per liter, but I don't want milligrams per liter. I want what? Nanograms per milliliter. So at this point, it really is just a somewhat complicated step-by-step unit conversion. So you can do this however you want. My little brain, though, likes to go in thousands. So I know that to go from a milligram to a microgram, there's how many? 1,000. There's 1,000 micrograms per milligram. So I'm going to convert my milligrams to micrograms by multiplying by 1,000. Then I can go nanograms is smaller than micrograms by 1,000. So to go from micrograms to nanograms, I need to multiply by 1,000. So now with those two steps in combination, all I have done is convert milligrams to nanograms. And that's where I need to be. Okay? So, and you can stop there, do that math, but remember that would be nanograms per liter. We still need to get rid of the liter. So the last conversion here is simply to convert liters to milliliters, because I know in 1 liter there's 1,000 milliliters. So if I divide by 1,000, liters will cancel, and my final units would be nanograms per milliliter. Okay? So if I give you that formula, and you know they were given 4 milligrams, and you calculated a volume of distribution of 57 liters, could you come up with 70 nanograms per milliliter as that concentration? That's the challenge that I'll put to you on a test, all right? You need to be able to come up, okay, here's my dose. That's what I just calculated for VD, and now I'm going to convert those units to the units that I need to get to. All right? Oh, is that a different formula? Or is it this formula rewritten? Because if I wanted to express dose, do you see where I could just cross multiply those? So dose, Cp equals dose over Vd, but dose would be equal to Cp times Vd. I still will give you these formulas. Don't freak out about that, but understand we're still messing with just one formula for me on this exam. In terms of the pharmacokinetics part, we're talking about the dose equals Vd times Cp or any rearranged version of that. Because now let's go the other way. We just took a dose and a volume of distribution to calculate a plasma concentration. Can we go backwards? If I give you a plasma concentration, can you go back and tell me what the dose was? Meaning if I give you this and you know that, can you figure this? Absolutely. So I'll show you my work here, but it's using the same formula but going backwards of what we just did. So what I'm going to start with here, obviously, is I need a Vd times a Cp. So here's my volume of distribution, okay? The only problem here is that my concentration is nanograms per mils. So the first thing I did was take my Vd and let's convert its units from liters to milliliters. So 57 liters times 1,000 gives me 57,000 milliliters. And I wanted that because then if I multiply that by my dose, my Vd times my Cp, right, milliliters cancel, and I will know my dose. But my dose at this point is in what units? Nanograms. And what do I ultimately want? Milligrams. So at this point, it really is just converting nanograms back to milligrams. So there is 1,000 nanograms per microgram, so I'm going to divide by 1,000. Then there is 1,000 micrograms per milligram. So if I do that and do that math all the way across, this concentration with that, given that volume of distribution, is the result of administering 2.5 milligrams. It's kind of cool to be able to give a dose and predict a blood concentration, or if you take a therapeutic concentration from a patient, work backwards to figure out what the dose was that caused it. But to be able to do that, you have to know the volume of distribution. To do that, the magic is that volume of distribution number. Okay? Next question. Let's move on. Oh, and I'm running low on time, so I'll go through this. Oxycodone, my favorite, no, I didn't say that. Oxycodone has a bioavailability of 68%, a term that we've already mentioned, a Cmax of 39.3 nanograms per mil. Max, C stands for plasma concentration. Cmax means the highest. Keep in mind, a lot of times when you give drugs orally, they'll peak and then they'll go down. So the maximum concentration you get at any point is at 39.3, and that occurs after about 3.1 hours after administration. I give you a volume of distribution. And now I mentioned this thing of elimination half-life at 4.5 hours, and something new also as well is a 45% protein bound. So let me just work through these. It says, what is the amount of drug absorbed in milligrams from a 40 milligram tablet based on the bioavailability? So again, if we're starting with a 40 milligram tablet, and I tell you the bioavailability is 68%, then you get 68 milligrams for every 100 milligrams absorbed. That means you absorb 27.2 milligrams. I said that's the amount that gets into the blood. So far, so good. That's what we've talked about. What we haven't talked about is not everything in the blood is available to go into the brain. For example, would you agree oxycodone to produce its effects has to go into the CNS? The problem is the drug, once it hits the blood, can get bound up by plasma proteins. And if it is bound up by a plasma protein like what? What's a common plasma protein that binds a lot of drugs? Albumin, very good, albumin. So some of the drug gets stuck on with albumin, it can't get absorbed. So that's where this becomes important, okay? Because now I want to know what is the amount of unbound drug, and why do I care about unbound? The bound won't produce an effect. It's the unbound that can then get into the brain. So if it's 45% bound by protein, how much is unbound? 55%. It goes back to the same idea. You'll get one of these values, but you may have to figure out the other, and it's either bound or unbound. So if 45% is bound, that means 55% is unbound. So that's why I'm going to take the dose that hit the blood, the 27.2 that we just calculated, and basically convert the 45% to the 55% and multiply it by that. So 55% of 27.2 is 15 milligrams. That's the active dose. That's the dose that can actually produce a biologic effect because it's in the blood and not bound up by the plasma proteins. So that's how you might have to use this idea of plasma protein binding. It's not difficult, but that's that idea. All right, now let's go on to something different. It says, what is the total amount of drug in milligrams present in a patient weighing 130 pounds at Cmax based on their VD? Oh, there's a whole lot there. But we know that essentially the dose is equal to the Cmax times the VD. So what was the Cmax? What was the VD? I've given you both of those values. They're just not complete yet, would you agree? And the units don't match. So let's get some work done here. So let's take 130 pounds, convert it to kilograms by dividing by 2.2, then take my non-patient specific volume of distribution and make it patient specific by multiplying it by their weight. So instead of 2.6 liters per kilogram, let's just call it 154 liters. Because I know the VD here times the concentration here is equal to the dose. But like we did before, liters is no good, so let's multiply by 1,000 to get milliliters, so that when I multiply by my concentration, my Cmax of 39.3 nanograms per milliliters, milliliters will now cancel, and I'm in nanograms. Divide by 1,000 to get micrograms, divide by another 1,000 to get milligrams, and we see 6 milligrams is our final amount there. All right, there we go. All right, so let me just show you this thing. It's kind of cool. Let's do this. Oftentimes you're said, well, how long before a drug is totally out of the system? Well, it takes a long time to get all of the drug out of the system. But we say typically 5 half-lives is enough time that most of the drug is gone, such that it's enough that you're not going to see any sort of therapeutic effect anymore. So how much percent is actually gone after 5 half-lives? What is a half-life? A half-life is the time it takes for the concentration to fall by what? Half, to go by 50%. So let's just do that. If we start at 100% and we have 1 half-life, what is it going to fall to? Here's 1. It goes from 100 to what? 50. So number 2 goes from 50 to 25. 3 goes from 25 to 12.5. 4 goes to 6.25. And the 5th one gets you to 3.125%. So after reducing and reducing and reducing by a half 5 times, you will only have 3.125% left. Roughly, you have lost 97% and only have about 3% of your dose left, all right? So in this case, it was asking how long for this particular drug. If we argue 5 half-lives means most of it is gone. If it's 4.5 hours per half-life, 5 times 4.5 means to get rid of nearly all of your dose of oxycodone, you have to get rid of, it would take 22.5 hours. But keep in mind, that doesn't mean it's all gone. It doesn't mean your drug test would be negative. Okay, let's not go there.